Sorry. So at least the first few lectures, I'm going to discuss modeling the transmission or the spread of infectious diseases. So here's an outline. So I'm going to begin today with sort of motivation and introduction. And this is going to take a while. I forget which slide the mathematics first appears on, but I think this is very important. So to give you insight, sort of philosophy, motivation, why model infectious diseases? Why is it interesting to biologists? Why is it interesting to mathematicians? What are the different types of models? What are the different types of pathogens? How does the body fight off infectious diseases? And so on. So I think maybe one slide on each of those topics is important to sort of set a background. Then I'm going to spend at least one lecture talking about the SIR model for directly transmitted infectious diseases. So a directly transmitted infectious disease is a disease like flu or measles, where if I have the flu and I cough on you, there's some probability that you're going to get the flu. But cholera is not an example. Cholera or malaria, those are indirectly transmitted infectious diseases. So if I have cholera and I cough on you, you're not going to get cholera, right? So the SIR model is the most basic so-called compartment model of which all the other models are built from. So I'm going to spend a lot of time talking about both the mathematics and also the public health implications from the mathematics, because it's the mathematics which form the, if you like, the theory or the framework for public health policy. Then, in a couple of steps, I'm going to extend the basic, hopefully I'm not using that. I'm going to extend the basic SIR model and the analysis, because this is mathematics, to what's called the SEIR model with vital rates, and you don't know what that is yet, but this is the current workhorse, so-called, in epidemiology. So if you pick up a paper on infectious disease modeling, it's likely to sort of begin with this SEI model with vital rates. Okay, then I'm going to talk about an application to measles and some of our recent work where we obtain what's called the transmission rate from the infective data. And again, you're not supposed to know what that means, but you will later. This is a problem that's been open for 60 years, 70 years, or something like that, and it's sort of an easy application of ODEs to solve. And then, at the end, I'm going to talk about also some recent work on modeling indirectly transmitted infectious diseases. And what I have in mind is cholera. And also, not just indirectly transmitted infectious diseases, but those with an immunological threshold. So bringing in some more realistic immunology. Let me just wait until I talk about that. So here are two quotes that I like very much about mathematical biology. The first is by Joel Cohn, who's a very distinguished population dynamicist. So mathematics is biology's next microscope, only better. Biology is mathematics' next physics, only better. And the second quote is by my Emory biology colleague, Bruce Levin. So Bruce is a very distinguished experimentalist. And I stress experimentalist. And this is a quote that he liked so much he recently put it on his webpage. Doing research in population biology without mathematical and/or computer simulation models is like playing tennis without a net or boundary lines. So Bruce will tell you that he doesn't know what experiments to do in his lab without mathematical models. And he's serious. Okay, this was a cartoon that some of my friends sent me. For a long time, I worked on fractals and multifractals. So when some of my friends heard that I started working in mathematical biology, this is probably what they thought I was doing, computing the Hausdorff dimension or the information dimension or things like that, but I'm not. Okay, so why model the spread of infectious diseases? So let me give you, I think, 4 reasons. Okay? So the first reason is that mathematical models can help to manage and control outbreaks. So models can test the effectiveness of control strategies and prevention strategies. So, how should Brazil, I guess the health ministry of Brazil, deal with pandemic influenza, H1N1? What should they do to prevent a spread? I don't know if there's technically a pandemic yet in Brazil. I guess there is in the world. But how should they try to control that? Should they close schools? Should they sort of stop big meetings like this? Well, it seems impossible to answer questions like that without a mathematical model. And actually, next week I'm going to, field cruise to discuss this with some researchers there. But let me just mention something that I do know a little bit about, and that's foot and mouth disease in England. So in 2001, there was an outbreak of foot and mouth disease in England. And this is a disease of cows. And it's a very serious disease because if you have a case, an outbreak in a country, then no other country will buy meat from that country. And it costs billions of dollars or euros or reais. So how do you contain an outbreak? Well, you can kill every cow in the entire country. And as long as the infective agent doesn't stay in the environment, which it doesn't in this case, that will end the outbreak. But of course, that's ridiculously expensive. So you want to kill the cows, say, on the farm. But then do you kill cows? They don't call it kill. There's a technical term, cull, which is to kill animals preventively. On neighboring farms, for a distance 1 kilometer, 5 kilometers, 10 kilometers, how far out do you go? There was also limited amounts of vaccine. Well, which cows do you vaccinate? So again, these questions you can't begin to answer other than to guess without a mathematical model. And at the time, Robert May, who some of you might know is one of the fathers of one-dimensional maps, was the chief scientific advisor to the British government. And he is one of the modern fathers of population dynamics. And he assembled several modeling groups from his former students and postdocs to actually model this outbreak. And I'm told that the government followed the advice of the modelers and that the outbreak was quickly contained. So that's kind of a success story. 2, mathematical models can elucidate mechanisms. So you're going to see this soon, probably the second lecture, with what's called R0, the basic reproductive rate. This is the key quantity for an infectious disease. Somebody tells you, they're studying an infectious disease or there's an outbreak, you want to know R0, and you'll understand very clearly why in the second or third lecture. Well, R0 is a number built from various parameters and an initial condition. And what Ross showed for malaria was that if this number is less than 1, then the outbreak will quickly, with exponential speed, die out. But if this number, R0, is bigger than 1, then you're going to have an epidemic. The number of infectives is going to grow. Now, it's essentially impossible to see this from data, to see this fact. So this is, and I'm going to present this very clearly, but this is a very nice application of a mathematical model to show a mechanism that you're very likely not going to see any other way. Okay, mathematical models help generate testable predictions. So this is the most important use of mathematics in all of biology. And most mathematicians don't know that. So if you just stop a mathematician outside and you ask her, what's the most important use of mathematics in biology, she'd probably say, well, to make very precise models of things. It's definitely not true. So mathematical models generate hypotheses. So it's much easier for a biologist studying a problem to try to verify or to refute a specific prediction rather than try to measure everything they can possibly measure and try to put it together. Okay? So many, probably most biologists who think about these things think of mathematical models as hypothesis generators. And then maybe most important for us is that analyzing mathematical models may lead, and I should probably write will lead, because it's already happened to me several times, to new mathematics. So this is how I first got interested in this business about 5 years ago. I was getting very bored with sort of the same small number of dynamical systems that many of us were studying, and I was looking for new examples of dynamical systems. And I got a few phone calls from various colleagues at Penn State where I was working, one a fisheries expert, one a wildlife biologist, one a demographer, and I quickly realized that these models are going to generate a lot of new dynamics. And again, I've already seen that in my research. Okay, so that's the positive. Let me talk maybe a little bit about the negative. And these are, what are the limitations of mathematical models? So this idea is due to Levin's, which is different from the Levin that I mentioned before, my colleague from Emory. So Levin's identifies three major attributes of a model. He calls them realism, precision, and generality. So realism means that the output of your model qualitatively describes the biological system. So you might have, might be studying, schistosomiasis in some population, and, over the long term, say 10% of the population is always infected, and you construct a mathematical model, and it shows that over the long term, 40% of the population is infected. Well, it's still telling you that there's endemic disease over the long term. So that's kind of realism. Precision is that the output of the model quantitatively describes the biology. So that means that, well, in real life, 10% of the population is always infected, and your model says, well, predicts 11% of the population is always infected. And then generality, of course, your model applies to many systems. And of course, if a model is precise, then it's realistic. Now, if you think about these, and there have been lots of papers written about this, especially by philosophers of science, they go crazy over this, it seems that you would want your model to maximize all three attributes. But Levin's claims that's not possible, that at best, your model can realize two of these attributes. Okay? So, for instance, I have some various projects with some biologists where we're trying to understand some general principles. Well, if you're trying to understand general principles, then for us, we care about realism and we care about generality, but we don't care very much about precision. On the other hand, I have a couple of projects with some infectious disease experts at the CDC. I should say one of the nice things about working in Atlanta is that the U.S. Centers for Disease Control, the CDC, is located in Atlanta. And many of the researchers there, and they have 5,000 researchers and physicians interested in infectious diseases. So I'm working with a couple of their groups. One project is with Shigella, which is a diarrheal disease. And they care about trying to understand things like the immunity after an infection and how underreported the disease is. So they don't care whether our model applies to cholera or to salmonella. They just care whether we're going to get new information about Shigella. So in that case, what they care about really is just precision. Okay, so what you care about depends on the questions, of course. Okay, so very briefly, here are the different types of models. There are deterministic models and there are stochastic models. For these lectures, I'm going to concentrate on deterministic models. Usually, if you have large populations, then it's fine to use deterministic models. If you have small populations, like Ebola in a village or something like that, you probably want a stochastic model. And I'm actually going to present quickly later on the stochastic version of the SIR model. Okay. One has continuous models and discrete models. Usually, if births occur continuously, say throughout the year, like for humans or bacteria, then a continuous model is fine. If births occur, it's in, say, all births occur, if you're thinking about fish or some insects, where, say, all births occur within a few weeks in the spring, then you probably want a discrete model. Okay, discrete models have built-in time lags and usually have more interesting dynamics. And then there are so-called analytical versus computational models. So analytical models tend to be low-dimensional models, either some type of dynamical system, discrete, or an ODE. There's something that you could sort of sink your teeth into. You can hopefully prove at least some things about. While a computational model is usually a huge model, frequently it's an agent-based model, you can very well, it's very useful to know dynamics to study such a model, but you're not going to prove anything. So for instance, Ross's original analytical model of malaria had 4 ODEs, or 2 depending on how you count, but the state-of-the-art model for malaria has 300 ODEs. Okay, that's a good difference between analytical and computational models. Okay, so what are the agents for infectious diseases? Well, there are 2 general classes. There are the microparasites and there are macroparasites. And for these lectures, I'm just going to concentrate on the microparasites. So these are the viruses, bacteria, protozoa, fungi. You know, so these guys are very small. You can't see them. If you have a virus, a viral infection or a bacteria infection, you have billions, at least, of virus particles in your body, right? Or at least billions of bacteria. So you have so many of these things that you can't count. They're very small. They have a very short generation time. So many bacteria, like E. coli, will reproduce in half an hour, 30 minutes. And it's a calculation that I just gave, actually, my 13-year-old daughter, to show that you start with 1 E. coli bacterium, and in 24 hours, if it keeps doubling in size and in number every 30 minutes, then what you will have is the size and the mass of the Earth. The microparasites complete their life cycle inside a single host, usually in a single cell. If you get a viral disease like measles, say if you weren't vaccinated, or chicken pox or something like that, when you recover, you're usually immune for life. Even flu, you're immune for life. The point is that flu evolves, the virus evolves so quickly, you're immune to that strain, but not to new strains. The duration of the infection is short compared to the human lifespan. You know, obviously a flu infection is a week, 2 weeks at most, compared to 80 years or so for a human lifespan. So usually to model infections caused by microparasites, one can just model the hosts. So on the other hand, there are the macroparasites. So there are the helminths, which are worms. There are the arthropods, which are like ticks or fleas or mites or what do you call the stuff you kids get in their hair? Lice. So down there is a picture of an intestinal roundworm and also the worm that causes schistosomiasis. It's the one in the red. So these grow, but they don't reproduce in the host. They're large. You can usually see them. They have a long generation time. They usually don't live in cells. They live in either on the skin or like in body cavities like the intestine, the gut. They usually don't kill people. They result in chronic infection. And to model these, it's more complicated because you need to model the sort of transmission in the host, but, I'm sorry, you need to model both the life cycle of the parasite and also the host. So these models tend to be significantly more complicated than models for microparasites. Okay, so viral diseases, influenza, measles, rubella, mumps, HIV, dengue, foot and mouth disease. Bacterial diseases, cholera, salmonella, gonorrhea, tuberculosis. Protozoan diseases, malaria, leishmania, African sleeping sickness, giardiosis. Okay, so these are all the diseases of which sort of SIR type models apply. Okay, now a brief history of mathematical epidemiology. So it didn't exist before like the 1850s. So before the 1850s, scientists thought that diseases like cholera and the plague were caused by breathing bad air. There's a name for this. I think it's called the miasma theory of disease. Now, it sounds completely crazy to us now, but it wasn't until the mid-1850s and the discovery of the microscope, when scientists saw germs, that they started realizing that these might be playing a role in the transmission of infectious diseases. Sort of one of my heroes is John Snow. So John Snow was a physician in London in the mid-1850s, and he was treating people during cholera outbreaks. Treating meaning watching them die, essentially. And again, up until then, people thought that people were getting cholera from bad air. But he realized that it's not the bad air, it's the water supply. And he famously removed the tap on the water supply, and that sort of ended the outbreaks. Now, he didn't know about bacteria. He didn't know about V. cholera bacteria. That took 30 more years for Robert Koch to identify, but he knew it was the water, something in the water that was causing the disease. By the way, if you're ever in London, in sort of the Soho, you can visit the John Snow pub, which is a nice pub, and they have the water tap outside that you can look at. Okay, then Ronald Ross in the 1910s created the first SIR type model of malaria. He's a very interesting guy. He won the Nobel Prize in Medicine for showing that malaria is transmitted by a mosquito. But he was also a sort of frustrated mathematician. So, I mean, he created these ODE models, and he was the first one to identify a threshold. I read that he also worked hard sort of on pure mathematics, although he was totally unsuccessable. But he created the first sort of ODE models in the flavor of SIR models. Then in the mid-1920s, Kermack and McKendrick actually studied what I call the SIR model. So the SIR compartment model was math action mixing, and they worked out some of the mathematical details. And then more recently, starting in the 1970s, Anderson and May, and both these guys are not just still alive, but they're still working. And over the years, they've had many very good students and postdocs. They've developed a comprehensive framework for infectious disease transmission models. So that's the history on one slide. Okay, now immunology on one slide. So how does the body fight off infectious diseases? Well, there are three basic ways. There are so-called physical barriers, like the skin. So most of us have some pretty bad bacteria on our skin. And that's fine as long as it stays outside. You know, we cut ourselves and the bacteria comes inside, that's bad. But the skin helps keep the bacteria and pathogens out. Okay? Also, anytime there's exposure of the body to the outside, like through the nose, the ears, the mouth, those cavities are lined with so-called mucous membranes, which filter out any type of pathogens. And in fact, I read that you have 2 football fields worth of mucous membranes in your body. Then there's the native immune system. So some of you might have heard of cells like macrophages, neutrophils, complement system, natural killer cells. So these act very quickly. And they better act quickly because if bacteria can double in number every 30 minutes, if this system didn't act quickly, you'd be dead quickly. So this acts very quickly, it's nonspecific, and it doesn't confer any long-lasting immunity. And then finally, there's the adaptive immune system, which consists of antibodies, so you might have heard T cells, B cells. So these take several days, usually 5, 6, 7 days to kick in, to start working. And this is completely amazing, because humans can form antibodies to anything, not just to any protein, but to any organic molecule. And I was telling Dr. Lopez before, the way they do this is related to symbolic dynamics. And I very much trying to find a student to work with me and an immunologist at Emory to try to study the symbolic dynamics behind this. But the point is that you can, it's completely amazing, but humans can produce antibodies to anything. And what's more is after the infection, they leave around some of these antibodies. Not many, but they leave around some so that the next time you're challenged with the same agent, you can beat it off very quickly, usually without even knowing it. So a very good research topic is to add more realistic immunology to existing transmission models. Because what I'm going to talk about, and even extensions of that, except for HIV models, have the most trivial immunology. The most trivial immunology. Let me skip that. Okay, so let's start talking about the basic SIR model. So again, this is a model of directly transmitted infectious diseases. So you think flu or you think measles. These diseases could be of humans, but they can also be of animals, and they can also be of plants. Okay, so this model applies to all three. And it's called a compartment model because what you do is you divide the population. And what do I mean by population? Well, it could be everyone in this room. It could be everyone in IMPA. It could be everyone in Rio. It could be everyone in Brazil. I mean, what a population is depends on the problem. But the idea is you divide the population, you partition it into three classes. The S class, which are the susceptible individuals. So those are the individuals that are susceptible to infection. The I class, which are those, the infected class, so those are the individuals that are currently infected. And the R class, which is what's called the removed class, so these are the individuals that have recovered or have died from the disease. Okay. In terms of units, I say let S of t be the number of susceptible individuals. Sometimes you'd like S of t to be the density of susceptible individuals. And sometimes, especially if you're talking about certain small animals or plants, you would like S of t to be the biomass of susceptible individuals. But we're going to just keep it simple and consider numbers of susceptible individuals and infected individuals and removed individuals. So this is sort of a schematic. So susceptible individuals are going to move into the infected class at a rate beta, or maybe you should say a rate beta times S, you'll see in a minute. And then infected individuals are going to recover at a rate nu. So this is the system of ODEs. So it's a system of 3 ODEs. You'll notice that it's nonlinear, but it's quadratic. So it's a polynomial system. I'll tell you now there's no closed form solution. You can't just write down the solution. On the other hand, I'm going to convince you, hopefully starting today and certainly next class, that essentially anything you want to know about this we can obtain from analysis. Okay, so let's look at the second equation. So this is telling you how the number of infectives is changing in time. So the second term tells you that, well, what the schematic said, that infectives are becoming removed. And if you don't mind, let me say recovered. Okay? At rate nu. That's all that's saying. What is this saying? Well, this is saying that new infections are occurring at a rate which is proportional to the product of the number of susceptibles times the number of infectives. And in the next slides, I'm going to explain things carefully, and it's very important that we understand what is beta, what is nu sort of precisely. So beta is called the transmission rate, and nu is called the removal rate. So let's focus in on this term, the beta times SI term. So that term is what's called mass action mixing or homogeneous mixing. And just think about it for a second. What does it mean? It means that if you have twice as many susceptibles, then obviously that number is twice as large. And if you have twice as many infectives, then that number is twice as large. So how could it be that the number of infectives is increasing at such a rate? Well, the only way that could be happening is if the infectives and the susceptibles are very well mixed. Right? Okay, keep that in mind. Why make this assumption? So when I'm sick, or yes?
What do you mean by well mixed?
Very intermingled. Again, you have to think about, so the rate of change of infections is if you double the number of susceptibles, then you double the rate of increase. And if you double the number of infectives, you double the rate of increase of new infections. And the only way that can happen is sort of the susceptibles are all very well mixed. I mean, you have to think about that a little bit. Okay, so what if you didn't have that? If you didn't have that, then you'd need to, if the mixing wasn't sort of homogeneous, okay, then you'd need a spatial model because you'd have different types of mixing in time and space. And that would make a model much, much more complicated. Now, you might say that's real life. It's probably true, but just don't say that yet. But without this assumption, so this assumption lets you write down an ODE rather than a PDE, or even something worse than a PDE. Okay. Is it true? Well, sometimes it's ridiculously false. So there was a study, and I'm not giving references to all the papers here. I mean, we're mathematicians. If anyone wants a reference, just ask me. So there was a study of gonorrhea spread in the United States, and it showed that 60% of all infections were caused by only 2% of the population. So, of course, here we don't have well mixing. Now, frequently, it sounds like a very stupid assumption. Certainly, when I'm feeling sick, I want to be home in bed. I don't want to be well mixing with all my friends. On the other hand, in practice, it's not as bad as it sounds, and there are ways of dealing with it. Okay? So you're going to have to trust me. I mean, there are many ways of dealing with it, with different infective classes and so on. In practice, it's not nearly as bad, usually, as it sounds. Okay, and again, I want to concentrate on this. I want us to understand the simplest model. Okay, so another very good research topic is to create infectious disease transmission models, or more generally, population models with more realistic mixing assumptions. And this is something that I'm working on very seriously. This is sort of one of my big meta projects. Okay, now what is beta? What is the transmission rate? The idea here is that each susceptible individual has some number of contacts. Let's call it kappa, contacts per unit time. Okay, now what is a contact? Well, contact depends on the disease. For flu, I have a contact with you if I cough on you or I sneeze on you. For HIV, it's a sexual contact, right? So contact is specific. So we assume, or the model assumes, that each susceptible individual has kappa contacts per unit time with other individuals. Now, we only care about the spread of the disease, so if a susceptible has a contact with a susceptible, it doesn't matter for the spread of the disease. So we just care about the proportion of those contacts with infected individuals. So the susceptible has kappa contacts per unit time, but only kappa times I over n are with infected individuals. And then we assume that the probability of transmission during each contact is tau. Now, if I have the flu and I sneeze on him from here, there's some probability he's going to get sick. If I move closer and sneeze on him, it's going to be a higher probability. So tau is some type of average probability. And again, this is the most basic model. Extensions of this, there are many extensions of this. There are books filled with extensions for modeling more more realistic betas. But again, I'm starting with the simplest model. So, so beta is then the number of contacts that a susceptible individual has with infected individuals per unit time times the probability of transmission. That's what beta is, so the very concrete terms. Now, it's been thought for a long time that beta is very difficult to measure directly, but I'm going to show you, third lecture, I think, that using a little bit of mathematics, it's pretty easy to do. What is new? Well, again, let's go back to the ODE. Sorry. So new is the rate at which infectives become removed. Oh, actually, I forgot to say something very important here. Let's go back to this model. What's a little bit odd about this model is there are no individuals. There are subgroups. So there's the susceptible subgroup, there's the infected subgroup, but there are no individuals having contact with other individuals. That's implicit. Okay? So this model has subgroups interacting with other subgroups. Like S interacting with I, right? I interacting with R, and so on. Not individuals interacting with other individuals. Those type of models are called agent-based models. And they tend to be more realistic, maybe much more realistic, but much, much more complicated. Okay, but I'm going to focus on these type of models. Okay, so in that case, nu is the rate at which infected individuals become removed. So that says that the duration of infection, how long people are sick, or individuals are sick, is 1 over nu. Make sense? Okay, so this simple model, I want to stress the assumptions. So built into the simple model, again, we're assuming that the disease transmission is direct. We're assuming that there are no natural births and no natural deaths, that the disease is what's called short-lived. Okay, the next step is to add natural births and natural deaths. Okay, but again, we're assuming here that the only deaths occur due to the disease. We're assuming that the infection has 0 latent period, which means as soon as you become infected, you become infectious. You're able to transmit the disease. For most diseases, you become infected, and then it takes some time for, say, the viral load to get sufficiently large for you to be able to transmit it. But this model is assuming that occurs instantaneously. And I mentioned at the beginning the SEIR model, and E is going to deal with, is going to be the exposed class to deal with this. We're assuming, again, this model assumes that recovered individuals have permanent immunity. They never become susceptible again. Okay? And this model also assumes that nobody is born with, say, immunity. That the only individuals with immunity are those that have recovered or been removed after they became infected. Okay, again, more assumptions. The model has no age structure, right? We talk about the number of infected. We're not talking about the number of infected from years 0 to 5 and 5 to 10 and so on. And it assumes that everyone has the same probability of getting infected. So some very old people who live by themselves in an apartment, they have the same probability of being infected that any of us here have. This is important. This model assumes that all individuals have the same immune system. Everyone is identical. So everyone has the same susceptibility to infection. So, some people are kind of sickly, right? They tend to get colds, flu, much more easily than others. Well, that's not built into this. And everyone has the same level of infectiousness once they're infected. Okay, again, these are usually not mentioned like this in books. And since we're doing mathematics, I think it's important to make this clear. And then lastly, the parameters, beta and nu, we're assuming remain constant throughout the outbreak. Well, very frequently, sort of public health interventions are going to change these numbers. So nu, remember, 1 over nu is how long a person is infected. Well, if you have a virus and you take, say, an antiviral drug, or if you have a bacteria infection and you take an antibiotic, that's going to reduce, right? You're going to get better. You're going to get better quickly. So that's going to make nu larger. But these models just assume that beta and nu remain constant. And again, extensions of this allow, in fact, I'm even going to talk about that, where beta is time dependent and so on, but I want us to understand the hypotheses of the basic model. Okay, so let's go back to the SIR model. This is it. You're going to see a lot of it for a couple of lectures. So how do you, let's go back here. How do we analyze this system? So what do we learn in ODEs to analyze a system of like this? What does Poincaré tell us? He tells us find the equilibrium points. What are the equilibrium points? Well, we set the 3 equations equal to 0. Well, the third one is kind of easy. That says I is equal to 0. How about S? Well, R, of course, doesn't appear explicitly, right? How about S? A little bit strange. So certainly if I is equal to 0, then this equation is 0, this equation is 0, this equation is 0, with no restrictions on S and R. So what this says is that all the points of the form S, 0, R are equilibrium points. So there's a 2-parameter family of equilibrium points. So the equilibrium points are very degenerate. And you don't find in ODE books how to study such ODEs. Okay? Okay, what's next? Okay, let's go back. Let's look at this system, and let's add up the 3 equations. Now, this isn't something one normally does with ODEs, but not only does sort of biology give rise to new dynamical systems, but it also has you look at maybe old differential equations from a new point of view. So never before I started working on population models did I ever think of adding up, at least I don't remember, adding up all the equations. So what happens if we add up the left-hand sides? ds dt plus di dt plus dr dt. Well, S plus I plus R is the total population at time t. Now, let's count. So remember, the removed class consists of those that recovered and those that also died due to the disease. If you count those that died as members of the population, which is a little bit strange to do, then S plus I plus R is the population size at time t. So if you add up these 3 equations, the left-hand side is just telling you how the population size is changing in time. Now, what happens when you add up the right-hand sides? You get 0. So what we just proved is that the total population, S plus I plus R, is constant. It doesn't change in time. So it's a conserved quantity or a first integral, whatever you want to call it. So this is property 1. The total population, S of t plus I of t plus R of t, is constant. Yes?
But what about dead people?
You're including dead people in here. You're including dead people. So before, I never know how to say this. I mean, it's kind of stupid to include dead people here. So it's probably better to say that you have an infectious disease which is going to kill very few people. So you assume that nobody dies and that the removed individuals recover. Then this makes more sense. But it's more general than that. Okay, so this is our first property. Second property, consistency of the system of ODEs. Something would be very stupid if, well, obviously we start off S of 0, the number of susceptibles at time 0, the number of infectors at time 0, the number of removed at time 0, are all non-negative numbers. Something would be very wrong if at some positive time, say the number of infectors became negative. Right? So it better be the case, if this model is to make any sense, that if you start off with non-negative initial data, then the solution stays non-negative for all time. Now, there are several ways of seeing this. Actually, there are several ways of seeing everything that I'm doing. The easiest way of doing this is to just rewrite the first equation. So divide both sides, take the first equation, divide both sides by s. So the left-hand side is the logarithmic derivative of s. The right-hand side is minus beta times I. Right? And then you just integrate. And you integrate, and you get, on the left-hand side, the log of s of t. And then there's an integration constant, which is the log of s of 0. And then when you integrate this, you get just minus beta times the integral from 0 to t of, say, I of s ds. And then you exponentiate everything, and you get that s of t is equal to s of 0, e to the something. Now, of course, e to the something has to be bigger or equal to 0. It has to be bigger than 0, sorry. So we see that this is a proof that s of t is bigger or equal to 0. Okay? The same thing for r of t, and then you use the fact that the total population size is conserved, so that I of t is equal to the total population minus s of t minus r of t. Okay, so that's a very simple proof of consistency. Next property. The limits as t goes to infinity of s of t, r of t, and I of t exist. So there's no oscillation. Why is this? Well, this is easy. Much of this is very easy. Let's go back to the differential equation. Let's look at the first equation. We know that s and I are both bigger or equal to 0, right? So that says that the right-hand side, remember the minus sign and beta and nu are positive, so that says that ds dt is less than or equal to 0 for all time. And the third equation says dr dt is bigger or equal to 0 for all time. Right? Now we know that the total population size stays constant. So we know that s of t, whatever it is, I showed you it's always bigger or equal to 0, and it's always less than or equal to the total population size. R of t, which is increasing, is always bigger or equal to 0, and it's always less than or equal to the total population size. So for s of t, it's an increasing function in time. No, I'm sorry, it's a decreasing function in time, but it's bounded between 0 and the total population size. So the limit has to exist. And the same thing for r of t, right? It's increasing function bounded between 0 and the total population size, so the limit has to exist. That clear? Okay, so here is some measles data from the UK from 1948 to 1958. This is before vaccination for measles. And this is the time series. This is aggregate data over several, I think, 8 big cities. And does it look like I of infinity, does it look like limit as t goes to infinity that of I of t exists? No, I of t is oscillating. So obviously, our simple SIR model doesn't apply or can't capture this oscillation in the number of infectives. It will start when we start making it more sophisticated. So this type of infection cannot be modeled by our most simple SIR model. What time should I go into? 5 minutes, okay. Fine. So just a short interlude about measles. So measles was a very common but actually fairly serious childhood viral disease. A vaccine became available in 1963, and there have been various excuse me, modifications, improvements of the vaccine, but even now it's only about 80% effective. You don't usually read this, but the vaccine is only about 80% effective. You read a lot about measles because there's a lot of data about measles in the UK and the US. These days, many parents aren't vaccinating children for measles because they're afraid of various types of side effects, and that has led to current outbreaks. So there are current outbreaks. Actually, there are cases in Brazil. I checked a few days ago. But it's becoming a serious problem again. So let me just end with property 4, and that is the disease dies out. So I claim that for all initial conditions, the limit as t goes to infinity of I of t is 0. So here's the proof. It's very simple. You go to the third equation. Okay? So you assume not. Okay? So look at that third equation. You assume not. So you assume that the limit is some positive number. So for t sufficiently large, dr dt is bigger or equal to nu times, say, that limiting value over 2. So that says for t sufficiently large, dr dt is bigger or equal to that value. Well, that says that the limit as t goes to infinity of r of t is infinite. But we know that that can't be the case, right? We know that r of t at any time is less than or equal to the population size. Okay, let me stop here.